Assalamualaikum. My name is Nur Aizaira binti Malaysia, and today I am going to present my media-based assignment for computer architecture, which focusing on detailed analysis of SRAM versus DRAM. In this presentation, I will cover the main characteristics of RAM, compare both types based on specific criteria, and justify their application in modern computer systems. Let's begin with the main characteristic of semiconductor random access memory or RAM. First, RAM has full read and write capability. This means it's possible both to read data from memory and to write new data into it, easily and repeatedly using electrical signal. Second, RAM is volatile. It must be provided with a constant power supply. If the power supply is interrupted, the stored data is immediately lost. Because of this volatility, RAM can only be used as temporary storage for the system workspace. Next, let's compare the two types of RAM, dynamic RAM and static RAM. In terms of construction, DRAM cells are built structurally simple, storing data as a charge on a capacitor and controlled by one transistor. On the other hand, SRAM is a digital device that stores binary value using traditional cross-connected flip-flop logic gate configuration, which require 4 to 6 transistors per bit. The structural difference directly affect their speed. DRAM is slower because the stored charge on the capacitor tends to leak away, meaning it requires continuous and periodic charge refreshing to maintain data. SRAM is much faster because it holds data statically if power is supplied, without needing any refresh cycle. Now, we look at storage capacity. DRAM is more compact. Its smaller cells allow more bits per unit area, making it less expensive. SRAM is less compact because its multi-transistor flip-flop configuration takes up much more physical space, making it more expensive. Finally, for power consumption, DRAM consumes more power because of the active supporting refresh circuitry. SRAM consumes less power when stable because no refresh is needed. Let's take a closer look at the physical layout of this memory by analyzing the typical memory cell structure. This diagram clearly illustrates why the two RAM types perform so differently. On the left side, we can see the dynamic RAM or DRAM cell. This design is much simple. It contains only one transistor and one storage capacitor. The transistor simply acts as a switch. When the address line is activated, the switch closes and allowing data bits to be written into or read out of the storage capacitor. Because capacitor naturally leak charge over time, this cell requires constant refreshing to keep its data. Then, if you look at the right side, we have the static RAM or SRAM cell. This design is much more complex. Instead of capacitor, it utilizes a total of 6 transistors labeled from T1 to T6. Transistor T1 through T4 are cross-connected to form a stable flip-flop logic circuit that holds a stable logic state under a constant DC voltage. Transistor T5 and T6 control the access to bit line B and its complement, bit line B prime, when the address line is selected. SRAM is the most suitable type for cache memory. This is because its digital flip-flop circuit structure provides the high-speed access required for cache memory. Cache memory sits right next to high-performance processor. It needs the best speed to serve critical CPU instructions immediately without requiring wait state. DRAM is the most suitable type for memory. Dynamic cell tends to be favored for large memory requirement. Modern operating system and application require gigabyte of data space. Because DRAM cells are smaller and less expensive, it is the best choice to build large capacity main memory cost effectively. In conclusion, there are always design trade-offs among speed, compactness, and cost. SRAM prioritizes extreme speed over compactness, making it ideal for small and ultra-fast cache memory. In contrast, DRAM prioritizes maximum compactness and lower cost over raw speed, making it perfect for large main memory. Both technologies work together seamlessly within the memory hierarchy to optimize the cost and performance of the entire computer architecture. So, that's all for me and thank you.